Moving on, we have the path planning and obstacle avoidance module. The goal of any path planning module is essentially to take the vessel and plan its path from a start location to a goal location while avoiding obstacles in its path. In order to do that, the AUV needs to have a good estimate of its current position as well as the data from the perception module has to be more. The key challenges for path planning algorithms will be the uncertainty in the sensor data as well as navigations of the dynamic environments, real-time processing and fast decision making, and there are variants of algorithms for static and moving obstacles. We also have various sensors which allow us to do obstacle detections as we discussed in the perception module. The information from these sensors needs to be combined and we need to know the location of the obstacles with respect to the AUV's location at any given point in time. This will allow the AUV to successfully plan its path to reach its desired goal location. There are three key types of algorithms that we can think of when coming to path planning algorithms. We can consider informed search algorithms, which will essentially aim to identify an optimal path from a start location to a goal location. And there are faster but non-optimal algorithms also, such as the rapidly exploring random trees. But these two can be classified as global planning algorithms. As opposed to this, we also have various local planners. One of the common local planners used in a lot of robotics is the artificial potential fields algorithm, which essentially encourages the robot or AUV to stay away from the obstacle using the philosophy of fields. Here, the idea behind the algorithm is I'm trying to simply explain it. Consider on the x-axis the distance of the AUV from the location of the obstacle. A typical APF field will have a variation of this sort. As you can see, closer to the obstacle, the value of the field is much higher, and further away, the value is much lower. This indicates that as the robot gets closer and closer to the obstacle, the field aims to push it further away from it with higher magnitude. This allows the AUV to stay away from its obstacle as well as simultaneously try to maintain its course. Now let's move on to the control systems module. Let's discuss the general idea behind any control system algorithm. Every control system works on the philosophy of having a desired state and an actual state, which I am denoting here with x, and a desired state I am denoting with xd. The job of the controller is to provide a commanded thrust command, which can also be considered as an actuation command. This actuation command will result in the AUV taking some action in its environment. This will result in a new state for the AUV, and that new state will again be passed with a new reference desired state, and the controller will keep on generating a new action for the AUV to track. This is essentially called the feedback loop. In autonomous systems. In case of control systems, various challenges include real-time actuations, uncertainty in dynamics. In case of AUVs particularly, this is a very important concern since the uncertainty in dynamics can lead to inaccurate controls, and which is essential to be corrected when implementing controls in a more stable manner. There are also concerns about noise and disturbances, external disturbances that can be present in the system. Some of the popular control algorithms to be considered can be PID control algorithm, which essentially considers this error factor. So the error we are defining as the difference between a current state and a desired state. A PID algorithm will use a correction factor based on proportional to this error, the derivative or the variation of this error over time, as well as the accumulation of this error, which is included in the integral term. A PID algorithm does not consider the actual dynamics of the vessel and hence may not be the most optimal action for that particular environment. A more advanced algorithm which can allow us to do a better navigation can be the model predictive control algorithm, but it's a bit more computationally expensive, so it's a trade-off between computation and accuracy in navigation. Various tools can allow us to effectively implement these control algorithms. MATLAB provides various control packages which will allow us to tune the gains for these PID algorithms, as well as even for effectively training the model predictive control algorithms. There are also various packages in ROS to implement these. Along with that, for most cases, it's a good idea to first test out various control algorithms in simulated environments such as Gazebo. And that brings us to the end of this module. So let's just summarize what we have studied in this module. First, we looked at the introduction of the need for an autonomous system. Then we also looked at the 4 pillars of autonomy. We looked at all of these 4 pillars, including the perception module, the navigation and control module, as well as we looked at the path planning module. We also looked at the details of various algorithms that are present in each of these modules, and we learnt that there are various tools out there which can allow us to easily implement these algorithms. So that brings us to the conclusion of this module. If you are interested in implementing these algorithms in real-world challenges, we have an exciting announcement coming up for you. So stay tuned.